Good morning, students. My name is Neeraj Tiwari. I'm from Electronics and Communication Department, TIT. And now I am going to lecture it on electromagnetic theory. Topic is boundary conditions. So far we have seen electric field intensity in the homogeneous medium. Homogeneous medium, that means it's a medium where you have a uniform electric field intensity. But now we are going to see electric field intensity in a different medium. So how you will calculate electric field intensity if you know the one side of electric field intensity. Now, these boundary conditions are very helpful in determining the field of electric field intensity of one side if the field of the other side is known. So, boundary conditions also dependent on the types of medium which we are using here. So, it will totally dependent on medium that is which is very looking like the dielectric 1 and dielectric 2. Basically, dielectric 1 and the dielectric 2 are the different medium, and we will see boundary conditions for the conductor and dielectric medium, and we will see boundary conditions for conductor and free space. So before going to discuss boundary conditions, first of all, we need to understand Maxwell equations. Maxwell's equations, which are very important while we are determining the boundary conditions. So first of all, the first Maxwell equation, which we all know that that is E dot dl is equals to 0, which is the it's a line integral. It's a closed path line integral. E dot dl is equals to 0. I am taking equation number this one 5.52. Now the second thing is that the same equation we have to represent in the closed surface. Closed surface, that means it will exist on a Gauss law, which is d dot ds is equals to q enclosed. Q is the surface charge density. You know what is the q enclosed? Q is the charge enclosed by the closed surface. And second thing is that you have to keep in mind all the electric field intensity in the one medium, you have to decompose into two parts. First one is tangential and second is normal. So how you will decompose electric field intensity? Et plus En, that resultant give electric field intensity E. There E, here you can see this equation you can write as E is equals to Et plus En. What is Et? Et is a tangential component of electric field intensity. And what is En? It's a normal component of electric field intensity. And what is E? It's a resultant of electric field intensity of both tangential and normal. In the same way, you have to decompose electric flux density, which is represented by D, which you can write as D is equals to dt plus dN. Now we are taking here the first type of boundary conditions, which is called dielectric 1 and dielectric 1. In dielectric 1, in this picture you can see this is in this picture you can see here is the boundary. Here you can see is the boundary. This part I'm assuming as a medium 1, and this part I'm assuming as a medium 2. So here we have to decompose electric field intensity, as I earlier told you, tangential component of electric field intensity, which is E1T, and normal component of electric field intensity, which is E1N. The resultant is given as E1 in the first medium. In the same way, second medium you can write in the same way, which is E2T. This is this tangential component of electric field intensity in the second medium, and U2N is the normal electric field intensity in the second medium, and the resultant of both is given by E2. You can see here, this is the E2. So medium 1 and medium 2, and this is the boundary, and this boundary is separated by a line. This line you can see here, A to B, B to C, and C to D, and D to A. So this line is basically known as it's a closed path. So when you are moving from A to B, it's how much length? It's a del W. And when you are moving from B to C, you know what is the length? See, what is the height of this B to C? It's a del H bar. It's a del H. It's a del H. And again, you can see C to, while you are moving C to D, it's a length of del W. So now we have to apply E dot DL in this figure. This is the A figure. In this figure, you have to apply E dot DL and write a complete equation. So how we will write a complete equation? See here. Here you can say E dot DL is equals to 0. So E dot DL is equals to 0. So 0 is putting here. Now the E dot DL. So E dot DL here is written E1T. So E1T, you can see it's a E1T. It's a tangential component of E1T, as you can see in this diagram. And E1T multiplied by the how much length is you can see here. It's a del W. When you are while we are moving from A to B, its a length is del W. So del W is multiplied by E1T. So what would be E1T into del W? Now we are moving from B to C. So field is going upward and we are moving downward. So what will happen? Minus sign will come here. So E1N into how much height? It's a whole height is del H. So half height would be del H by 2. So what will come? What will come into account with minus sign? E1N into del H by 2. So you can see in this diagram, in this equation, see in this equation you can see E1N into del H by 2. Same what I told you. Now the same equation you can write as while following the path, and finally you will get like that equation. So if you simplify this equation, you can get E1T is equals to E2T. So clearly you can see tangential component of electric field intensity undergoes no change across the boundary. Means tangential component of electric field intensity undergoes no change across the boundary. So that's what 5.57 says. Now now I'm talking about if we have E1T is equals to D2T. So we already know that what is the relation between electric field intensity and electric flux density D. So what is the formula? It's a D is equals to epsilon into E. So E1T you can write as D1T upon epsilon 1. So what you can see here, that's what I'm saying. D1T upon epsilon 1. So E1T is equals to E2T. That means what you can write as D1T upon epsilon 1. So in the same way, E2T is equals to D2T upon epsilon 2. If you simplify this equation, you will get D1T upon epsilon 1 is equals to D2T upon epsilon 2. So clearly you can see electric flux density undergoes some changes across the boundary. Hence, duty is said to be a discontinuous across the boundary. Clearly, you can see it's a D1T upon epsilon 1 and D2T upon epsilon 2. So here you can see electric flux density undergoes some changes across the boundary, or duty is said to be a discontinuous across the boundary. So what is we conclude from this equation? Now the second Gauss law. Now the second Gauss law we have to apply. What is Gauss law? It's a D dot ds is equals to Q enclosed. D dot ds is equals to Q enclosed. So what is Q here? What is the Q here? Q. What is del Q? What is del Q? Del Q is a del S into rho S. Rho S into del S is called del Q. So how much charge is enclosed by the surface is del S into rho S. What is rho S? Rho S is a surface charge density. It's a surface charge density. So how you can write? See the second diagram. See the second diagram B. In this diagram you can see. Here is a closed surface, and tangential component will not exist here. It will exist only tangential component, sorry, normal component. So what will happen, in upper side you will see d1n, and downside you will see d2n. So what will happen, d1n minus of d2n is equals to rho s into del s. So that kind of equation you are getting from this diagram. This is the number 2 diagram in the section B. So it's a d1n minus of d2n is equals to rho s. So finally, this equation, how we are getting this equation? We are getting this equation from the Gauss law, as I told you. What is Gauss law? It's a d dot ds is equals to q enclosed, and q enclosed is written as a del q, which is rho s into del s. And finally, you can write as Gauss law d1n into del s minus of d2n into del s from the previous figure what I told you. So finally, if you simplify this equation, you can get d1n minus of d2n is equals to rho s. What is rho s? Rho s is the surface charge density. So now, so we have to assume here it's a charge-free region. Charge-free region, that means rho s would be 0. So charge-free region rho s would be 0. In that case, d1n is equals to d2n. So finally, you will get d1n is equals to d2n for charge-free region. So clearly, you can see electric flux density. Here you can see normal component of electric flux density undergoes no changes across the boundary. Here you can see normal component of electric flux density undergoes no changes across the boundary, or it is said to be a continuous across the boundary. Simply, as we know that d is equals to epsilon into E. So simply you can write as E1n into E1 epsilon n 1 and epsilon 2 into d2n. So simply you can see here electric field intensity goes some changes across the boundary. So I would say normal component of electric field intensity undergoes some changes across the boundary. So all the equations we are getting from the boundary conditions. As we have seen, this is the normal component of electric field intensity, which is undergoes some changes across the boundary. Now what is the second use? Now the second use of what is the second use of boundary condition? The second use of boundary condition is to determine law of refraction of electric field intensity across the boundary. So when you are determining law of refraction, you can use the boundary condition. So I'm using here, as we know that E1t is equals to E2t. So finally E1t, what you can write as E1t is equal to E1 sine theta 1. From where you can write as you can write from by looking this diagram. In this diagram, it's a E1t and it's a D1t, and normal component of E1 and normal component of D1, and the resultant I am getting E1 and D1. In the first medium, this is, and in the second medium, likewise we can see D2t and D2n and D1t and D2n. So what is theta 1 and theta 2? Theta 1 and theta 2 are making angle from the boundary, making theta 1 making angle from the E1, and theta 2 is making angle from the E2. Theta 2 making angle from the normal to the theta 2. So what you can write? So what equation you can write by looking this diagram? It's a E1 sine theta 1 is equals to E1t equal to E2t is equals to E2 sine theta 2. As we know that sine theta is what? Sine theta is perpendicular upon hypotenuse. So you can easily calculate by perpendicular upon hypotenuse from the previous diagram what I have shown you. So finally you will get E1 sin theta 1 is equals to E2 sin theta 2. And the second equation you will get from the previous figure, what I have shown you. It's cos theta. As we know that cos theta, what is cos theta? It's a base upon hypotenuse, base upon hypotenuse. So you can simply determine cos theta 1 from the previous figure, which is d1n and is equals to d2t. You can write epsilon 2 into e2 into cos theta 2. So basically, if you simplify this equation, you will get this kind of equation you will get. So finally, if from this equation, suppose this is the equation number 1 and this is the equation number 2. If you divide equation number 1 from 2, then you will get tan theta 1 upon epsilon 1 is equals to tan theta 2 upon epsilon 2. So basically, if you simplify, tan theta 1 upon tan theta 2 is equals to epsilon 1 upon epsilon 2. So this is the so this is what I am talking about. Tan theta 1 upon tan theta 2 is equals to epsilon r1 upon epsilon r2. So this has from where this has come, you know, it's a as we know that epsilon 1 is equals to epsilon naught into epsilon r1. So epsilon naught will cancelled out. So epsilon r1 and epsilon r2. So easily we can see it's a tan theta 1 upon tan theta 2 is equals to epsilon r1 upon epsilon r2. It's a clearly, this is the law of refraction of the electric field intensity at the boundary at the charge free region where the rho s is equals to 0. Okay, thank you class. And tomorrow we will see boundary conditions for the dielectric and conducting medium. Okay, thank you class.